Welcome back. In this video, we're going to take a different view of matrix multiplication. Up to this point, we've thought about matrix multiplication on the right-hand side. We started off with the idea of a 2 by 2 by a 2 by 1, okay? And I think it would probably be good for me to go back to that. At first, we said that when we multiplied a matrix like 1, 2, 3, and 4 by the vector 5 and -6, we took 5 of the first column, 5 of 1 and 2, and we added it to -6 of the second column. So it's -6 of 3 and 4. And so if we, put that all together, that was 5 minus 18 is going to be -13, and 10 minus 24 is -14. And then when we were, moving it up to the idea of multiplying 2 by 2 by 2 by 2, the whole idea was that we just did the same thing. It was just the first column of our answer was going to be, what we would get by taking 0 of the first column and 2 of the second column. And then the second column would be what I would get by taking -1 of the first column on the left and none of the second column. Okay, so that's kind of a review of where we were on matrix multiplication up to today. Now we're going to talk about multiplication on the left, but I'm going to remind you that the same rules are going to apply, specifically with the dimensions of the factors and the product. Okay, so if we're going to multiply an m by n by an n by p, numbers in the middle have to match, and the product will be m by p. All right, so I want you to think about, just doing this left multiplication, the vector times the matrix, however you normally would. I will point out, though, that, if I'm thinking about a vector that's just one row and 2 columns multiplied by a 2 by 2 matrix, that should give me back a 1 by 2 row. Okay. So just thinking about this and doing this however you normally would, I want you to think about it for a second. Do it on a scratch sheet of paper, do it on your notes. Then write down your answer, check against mine, stalling. And 57 and -33. Okay, and maybe you can see something different in that, okay, but I'm going to just hold that there, just not really give a whole lot on that, and then I'm going to talk about matrix, 2 by 2 by 2 by 2. This should still give us a 2 by 2 back. And if we do this the old way, 9 of the first and 2 of the second, it's like, okay, 9 and 7. And then on the second column of the product, 10 of the first column plus 2 of the second column on the left, so that'd be 10 and 8. What happened here? That what's happening when I multiply on the left, 5 of the first, 7 of the second up top. And then in the second example, 1 of the first and none of the second. And then taking 1 and subtracting another. Left multiplication is working on the rows of a matrix the same way right multiplication works on the columns. Let me show you what I mean. First example, I took 5 of the first row and added it to 7 of the second row. Down lower, if I think about just the first row of the product, the first row of the product is I copied the first row and ignored the second. That's why I see that 9 and 10 repeated. And then the second row of the product down here is where I take 1 of the first row and I subtract 1 of the second row. 9 minus 2, 10 minus 2. So once again, the key message here is that left multiplication acts on the rows of a matrix. All right, now moving on, thinking about a situation where y is a 2 by 2 matrix and we're going to multiply x times y, and we know x. So we know the thing we're multiplying on the left. Describe x times y in terms of the rows of y. All right, well, if I'm trying to do x times y, I'd have 1, 0, 0, 2. Actually, I need to do that in black. 1, 0, 0, 2 multiplied by something with 2 rows. And now I'm going to just call it a red row and a blue row. I'm just going to say with no loss of generality that the red row's on top. Okay, now, if I'm thinking about it this way, the first row of the product is going to be, I'm looking at right here, the first row on the left, 1 of the red row plus 0 of the blue row. Okay, 1 of the red row, none of the blue row. Okay. And then the second row of my product is going to be 0 of the red row plus 2 of the blue row. And I'll just leave that there. Okay, then the next one, 0, 1, 1, 0. It kind of looks like the identity matrix, but worked around some. So 0, 1, 1, and 0. And I'll come back and I'll describe these with words here in a moment, but I'm coming to a point. And okay, if I'm multiplying that on a red row and a blue row, okay, the first row of the product is going to be 0 of the red row plus 1 of the blue row. So I have here. And then the second row of my product is going to be 1 of the red row and none of the blue row. So that served to like kind of flip the 2 rows. And then the last one, okay, 1K01. Okay, that's interesting. Multiplied by a blue and a red, or a red and a blue, pardon me. Okay, first row of the product is just going to be 1 of the red row, none of the blue row, so that'll be easy enough. My product is going to be k copies of the red row added to the blue row. So I'm going to just say, okay, I'm going to have the blue row, and I'm going to add k of the red row. About it and kind of write some word descriptions of what just happened here. Okay, so to recap, in A, I doubled row 2, right? I ended up with just 2 of the blue row, but otherwise it kind of looks the same. So I'd say multiplied row 2 by 2. In B, I can see what ended up happening was I swapped the 2 rows. And in C, I added k copies of row 1 to row 2. If you think this kind of sounds familiar, these are the row operations. So what we're about to do is we're about to connect the idea of left multiplication to the idea of row reduction that we've been working on recently. All right, so for the past, week or two, you've been really working on your row reduction in this class, and you've built this skill, and we're going to use it over and over again. But it's going to be nice for us to kind of connect this idea back to the idea of matrix multiplication, which is kind of where we started. Okay, so if you think about what the first step of elimination is going to be, it's going to be subtract 3 copies of row 1 from row 2. And if I do that, that's the matrix I'll get, but I actually want to write the reduced matrix as a product. Okay, so I'm going to just say start with step 1, row 2 minus 3 of row 1. But I'm going to rewrite this as negative 3 of row 1 plus row 2. So I think you'll see why I'm going to be interested in doing that. Okay, I'm going to need an elimination matrix. And I know I'm bumping it up to 3 by 3 here, but I'll talk you through it. So the first one is, it's going to be a 3 by 3, right? Because we're going to be operating on these 3 columns. And if you really start with the idea of the 3 by 3 identity matrix, it makes it a lot easier. Now, I am going to need to make this a little bit smaller, I think. Possibly move it up here. All right. But what's going to happen is think about it row by row. I did nothing to row 1. I did not change row 1, so it should have the same row as the row 1 of the identity. Also, you could think about this. I took 1 of the first row, none of the second row, and none of the third row, and that's what I got right here in the first row of my product. Okay, the second row is where the action happened. I added -3 of row 1 plus 1 of row 2, and I ignored the fact that there was a row 3, right? I didn't do anything with 1651. So I'm going to say my third row of my product right down here is 0 of the first row, 0 of the second row, and 1 of the third row. And we're going to call this elimination matrix E21. Now we're going to call it E21 because it introduced a 0 into the 2-1 entry over there. Okay, and we're going to be systematic about this because of what we're going to do with this in the next video when we go to decompose a matrix into the product of 2 triangular matrices, like factoring. Okay, so if I'm going to do this, I'm going to say, really what I just did was I took 1 and -3, 0, 0, 1, 0, 0, 0, 1, and I multiplied it by my original matrix. Even copy the vertical bar if we like. 3, 14, 7, 10, and 1, 6, 5, 1. Okay, there we go. And you can check that with matrix multiplication however you want, the old way, using a calculator, whatever you want. But you can see that that's going to be valid. Okay, now I need to think about step 2. What am I going to do next? I'm going to want to clear out that entry down here. I want to get rid of that entry in the third row and first column. So if I subtract 1 copy of row 1 from row 3, that will clear out the entry in the bottom left. If I think about what I just did there, step 2, I took row 3 minus row 1, but I'm going to write that as the negative of row 1 plus row 3. And then I'm going to write my elimination matrix. I am going to call that one E31 because it cleared out the 3-1 entry of the matrix. Okay, didn't do anything to the top row, so I'm just going to leave that there, 1, 0, 0. I didn't really do anything to the middle row either, so I'm going to call that 0, 1, 0. And then I'm going to say, all right, well, what I did was on the third row of the product, right here, I got that by taking -1 of the first row and adding it to 1 of the third row. So I'm going to say, all right, really what this has got going on is 1, 0, -1, 0, 1, multiplied by the previous matrix, which I could have looked at as E21 times the original. But we'll get there with stacking them all up in the future, maybe even in the last example in this video. So if I just copy that down, 4, 1, 6, 5, 1. Okay, that would be true. Now at this point, you're probably looking at it and saying, okay, I can see that the system you're trying to solve has no solution. You have 2, 4, 4 and 2, 4, -1, and those aren't parallel, so you're going to end up with an inconsistent system. And that's true. And what we're going to be interested in mainly here today and in the next lesson about factorization is square matrices that correspond to unique solution scenarios. So if we can't reduce to an upper triangular matrix with non-zero entries on the main diagonal, we're not going to be able to obtain a unique solution, and that's not exactly the case we're going to be interested in. Okay, we've already seen matrices like that. If we can't reduce to something like this, the matrix was not going to be invertible earlier in this unit. Okay, but I think for now, I think that's as far as I want to take this example because we can see it went to no solution. Let's look at one that we can reduce all to upper triangular. So for this example, I'm going to just show you all the row reduction steps to take it down to upper triangular. Okay, I'm going to start with adding 1 copy of the first row to the second to introduce a 0 there, and then I'm going to introduce another 0, and then I'm going to get a third, right? It was really convenient that I had 5 and 5 there. I was able to subtract. Okay, but we'll go step by step. We'll be systematic. We'll say the first step was I added row 1 to row 2. So we need an elimination matrix for that, but we'll be able to figure that out. Okay, so what we did was we multiplied something by A on the left, right? That's kind of the key idea here, is that row operations are left matrix multiplications. So I added row 1 to row 2. I didn't change row 1 at all. Did I change row 3? So those should have the same rows as the identity matrix. What happened was I added row 1 plus row 2. Okay, so that would be the middle row. And it's the middle row because it produced that row right here in the product. Okay, and I am going to call that E21, and just to keep track, I'm going to call that E21A. And then for the next step, I added 2 copies of row 1 to row 3. So didn't change row 1, did not change row 2. Row 3 was 2 copies of row 1 plus, didn't consider row 2, plus 1 copy of row 3. Okay, and then we're going to multiply that, and that's going to be called E31. We multiplied that by E21A. And I want to write this in, E31, E21A. Right, and then my last step was I canceled off the 5s, right? I could see that happening. I subtracted row 3 minus row 2. So I need to think about row 3 minus row 2. Really, that's -1 of row 2 plus 1 of row 3. And I didn't change the other rows, so they have the rows from the identity matrix, which is kind of like the do-nothing matrix. And I multiplied that on E31, E21, and A. And we are going to call that last elimination matrix E32 because it cleared out the 3-2 entry. Now, I have got this matrix reduced down to an upper triangular matrix. So, where we're going to leave it off today, just, okay, we've seen we can do elimination matrices. I might have you do some practice on that here sometime soon. But I've got this matrix here, which is upper triangular. We're going to call that one U. And if I were to combine all 3 of those elimination matrices, notice those are all lower triangular matrices, I could multiply them together and get a matrix E, just like a general elimination matrix. Now, we're not going to be all that interested in matrix E. We're going to be much more interested in the inverse of matrix E, but that's in the next video. And so for now, we're just going to kind of leave it here, say that, okay, we've reduced to an upper triangular matrix in echelon form, and we were able to write it as the product of our original matrix multiplied on the left by a series of elimination matrices. So that's going to be all for this video. Thanks for watching.